Howdy, let's go ahead and look at Chapter 11 in the 5th edition of the Practice of Statistics. This is Inference for Distributions of Categorical Data. We've talked in some previous chapters about quantitative data, whether we've got single sample or two sample procedures, and we've talked about those with hypothesis tests and confidence intervals. We also talked about proportion problems where we could deal with single sample proportions or two sample proportions, but sometimes we've got more groups than that, and that's what we want to look at in Chapter 11. So the first section is called the chi-squared goodness of fit test. In this section, we'll learn to state the hypotheses and compute expected counts for the chi-squared goodness of fit test. We'll talk about calculating the test statistic. It's the chi-squared test statistic. It uses degrees of freedom and comes up with a p-value again. All those things come together to perform a chi-squared goodness of fit test, and then we'll talk about the follow-up analysis on understanding what those results mean when they are statistically significant. Sometimes we want to examine the distribution of a single categorical variable in a population. The chi-squared goodness of fit test allows us to determine whether a hypothesized distribution seems valid. So what am I talking about here? Well, we can decide whether the distribution of a categorical variable differs for two or more populations of treatments using a chi-squared test for homogeneity. And that will organize the data in a two-way table. And then finally, we can also use the information in a two-way table to study the relationship between two categorical variables. The chi-squared test for independence allows us to determine if there's convincing evidence for an association between the variables in the population at large. This is three different things we're going to look at: the chi-squared goodness of fit test, the chi-squared test for homogeneity, and the chi-squared test for independence. The first section, the one I'm looking at now, discusses the chi-squared goodness of fit test. The chi-squared test for homogeneity and independence will come in the second section. They look nearly identical, those two, and they've actually all three got very comparable ideas behind them. In a chi-squared goodness of fit test, we start with our data in a list or in a single row or column of a table. For the test in homogeneity and independence, we end up with what they call a two-way table, but basically a table that's got variables or categories across the top and down the side. So let's look at the chi-squared goodness of fit test. According to M&M Mars, here's what they say the new mix of colors is for M&Ms. 13% will be brown or red. 13% brown, 13% red, 14% yellow, 16% green, 20% orange, 24% blue. We opened a bag of M&Ms. There were 60 M&Ms in there, and here's what we got. Divided them out by color, and there's what we got. In my sample, I had 9 of the 60 M&Ms were blue. That's 15%. That's a little bit different than the 24%. And I could go through and figure that out for each of these. The question is, I don't just want to know, is the 9 or the 15%, the 9 blue ones, different than this, but is it reasonable to think that all of these come from a distribution that looks like this or not? In a previous chapter, we would do a one sample test to look like that. Is the proportion of blues 24% or is it different than 24%? And I could go through and perform my test. However, I don't really want to do that 6 times for this data, and that's where the chi-squared goodness of fit test comes in. The chi-squared goodness of fit test will take into consideration the entire bag at once, because clearly, let me back up a little bit, clearly if I have more blues, I have fewer something else's because there's a limited number of M&Ms in the bag. So these categories here are not all independent of each other. More in one category necessarily means fewer in another category. In a chi-squared goodness of fit test, I'll state my null hypothesis in a sentence. And here it's the company's stated color distribution for M&Ms is correct. The alternative is going to be that it's not correct. I don't have to make a supposition about what color occurs too much or too little. I just say it's like we expected it to be, or it's not like we expected it to be. We could use symbols, but this gets a little bit laborious in my opinion. I would prefer a sentence. There's just a lot of stuff to process for my brain and a lot of places where I can make a mistake. So although this is technically correct, it's not really my preferred method of doing it. Now, the idea of a chi-squared goodness of fit test is this. We're going to compare what we actually observed with what we would get if HO is true. The more difference we see there, the more evidence that HO it should be rejected. Let me say that again. I'm going to compare what I actually observed to what I would expect to get if this HO is true. The greater the difference between the observed values and those expected values, the more evidence we have against HO. So assuming that the distribution that M&M Mars told us is correct, 24% of the M&Ms are blue, we got 60 M&Ms. That gives me an expected value of 14.4 blue M&Ms. Similarly, taking all those percentages and multiplying them by 60% gives me this table. And this is easily done in my list. If I put these percentages, say, in my L1, and then in L2, I just multiply L1 times 60. Not surprisingly, if I add up all these numbers right here, I'm going to get 60. Because if I add up all these numbers right here, well, actually, I don't. Oh, yeah, because the 24 is not listed on here. So if I add all these numbers up, along with the blue one as well, I'll get 100% of the M&Ms. So these numbers plus that 14.4, they need all 6 of them on there, all 6 colors, is going to be 60 M&Ms. It's okay that these numbers right here are decimals, even though we don't necessarily expect fractions of M&Ms, and that doesn't mean that we can't get broken ones in the bag, but that's not really what we're expecting here. So decimals are just fine. Here then is a table of all of them. So here's what I got. This is just copied from that original table. And these expected counts right here, it's that 14.4 plus these other numbers that I got right here. So here's what I observed, and here's what I expected. Now, just like before, when we took x bar minus mu, or p hat minus p, I'm going to take my difference between these observed and expecteds right here. They've made a graph and want to see if these orange expected numbers are statistically significantly different than these purple observed numbers. Of course they're different. The question is that difference something that could reasonably be attributed to chance, or is it because maybe those percentages that M&M Mars gave us weren't true? The book describes it like this. We see some fairly large differences between the observed and expected counts. How likely is it that differences this large or larger would occur just by chance in random samples of size 60? Because your bag of M&Ms is basically like a random sample of M&Ms from the M&M Mars Company. We're going to calculate the chi-squared test statistic, just like we've done z-test statistics and t-test statistics. But the formula looks like this. It's the observed minus expected, the observed minus the expected, just like x bar minus mu or p hat minus p. Then we square it and divide it by the expected, add them up, and that gives me my chi-squared test statistic. So let's look at this in table form. You can see each of these numbers here that are color-coded according to the color of M&M. How about that? So the blue is observed, that's 9, minus expected, 14.4, squared, divided by expected. 8 minus 12 squared, divided by 12. 12 minus 9.6 squared, divided by 9.6, and so on and so forth. This would be easily done in my calculator using my lists. I'll go through a function as well. These numbers add up to 10.180. Now, this is the chi-squared test statistic. And I think we can see if these numbers were further apart, if my observed and my expecteds were much more different, then each of these little boxes would be much bigger, and this chi-squared test statistic would be even bigger. The smaller this value is, the closer these numbers are to each other. The bigger this value is, the further these numbers are from each other. But we can use this along with a table to figure out the p-value. That's what I just said. We go back to degrees of freedom with the chi-squared test statistic. The chi-squared distribution uses the concept of degrees of freedom, and that's what we've got right here in this table. You can see the larger the degrees of freedom, the more normal looking the graph is, but nevertheless, it's still right skewed. Degrees of freedom for this problem, for these chi-squared problems, are the number of categories minus 1. So in this problem, I had 6 different colors. So it's 6 minus 1. This problem has 5 degrees of freedom. And it may make sense to you like this. If I have a lot more categories, I'm going to end up with a lot more things over here to add up together. So I've got more degrees of freedom, more room to have mistakes. So I've got to incorporate all of that. Now, the reason that we have degrees of freedom in here is because only a certain number of these M&Ms are free to change. If I've got 60 M&Ms in the bag and I told you what 5 of these categories were, you would know how many there were in the 6th category because it's whatever adds up to 60 M&Ms. And so that's why the degrees of freedom concept comes back upon us. So in this problem, they also go through on this slide that one of the conditions for chi-squared tests is that all of the expected counts need to be at least 5. All of the expected counts need to be at least 5. And you can tell from this graph that the chi-squared distribution starts at 0 and it's always positive. The reason for that is because these numbers are always going to be positive. The expected counts, the thing that's on the bottom, is always a positive number. I don't expect to get a negative number of a color of M&M. And these things on the top are always non-negative because they're squared. They're usually positive. If I got exactly what I would expect, then the top would be 0. But these individual counts can never be negative, so they're never going to add up to be something that's negative. So we've got 5 degrees of freedom. My chi-squared test statistic was 10.180. And so I can draw a right skewed graph. It's written like this, chi-squared, and sometimes there'll be a little subscript right here, a subscript of 5 to tell me that it's got 5 degrees of freedom. This blue area is my p-value. And so I can look on my chi-squared table for the 5 degree of freedom row, and I go over until I see that. So it's between these two numbers, which tells me that my p-value is between those two numbers. If I have an alpha level of 5%, my p-value is bigger than that. I'm going to fail to reject HO, and I do not have sufficient evidence to challenge the Mars claim of the color distribution. So let's look at the conditions necessary for this. First of all, I already mentioned this one right here. Large counts, all expected counts are greater than 5, the expecteds. So when I look at that problem, I look at the expected values and make sure they're all bigger than 5. We, of course, always need the random. And if I'm sampling without replacement, I want to make sure I get less than 10% of the population. So generally those are met. I just want to address them again and make sure that we acknowledge those as we're doing problems. 2 words of caution here. The first is the chi-squared test statistic compares the observed and expected counts the actual number of M&Ms, not the proportions in each category. So we're actually dealing with the counts there, not the proportions. Be careful on that. And also note that this large count is that the expecteds are all bigger than 5. Not that the observes are bigger than 5, that the expecteds are bigger than 5. So you could kind of think about it like this. Before I even start the problem, if I want to use a fun size pack of M&Ms to challenge the claim of the proportions, I'm not going to be successful because there's not enough M&Ms in that bag to expect to have 5 of each color. So when I don't get 5 of each color, I'm not really surprised. It's because the bag is so small. Even before I've ripped the bag open, I can already tell you there's not enough M&Ms in that bag, which makes you wonder, of course, why they call it the fun size pack when it's so small. That giant party pack seems like the fun size one to me. Anyhow, I digress. So here is a synopsis of what we just said on the chi-squared goodness of fit test. Suppose the conditions are met. To determine whether a categorical variable has a specified distribution in the population of interest, express the proportion of individuals falling into each possible category, perform a test of HO and HA. HO, the stated distribution is correct. HA, it's not correct. Ditto marks are okay. I usually use ditto marks on HA and then put a capital not in there and underline it so it's real clear which one is correct and the HA is that it's not correct. Then we're going to find the expected counts for each category, the percentages that I got multiplied by the sample size. And then I calculate the test statistic with this formula, observed minus expected squared over expected. However many categories I've got, it's that minus 1 for the degrees of freedom. So again, it was 5 degrees of freedom here because I had 6 categories minus 1. Some young stat students will want to make this a 59 degree of freedom problem because there were 60 M&Ms. That's not the way it works with chi-squared. The p-value is always the area to the right under a chi-squared distribution. It's always the area to the right, which is the way it's shaded on your chart. If you look at your chart, that's shaded to the right, so there's no need to subtract from 1 or anything like that. So let's look at another problem. This is a really interesting problem from a very interesting book. I would recommend it. I found it to be a great read. Malcolm Gladwell's book, Outliers. And in that book, he notices that there seems to be a connection between the age of a hockey player and how good they are. So specifically, in Canada, January 1st is the cutoff league for youth dates. And lots of national NHL hockey players come from Canada. So players born in January have the age advantage. Older players tend to be stronger, bigger, more coordinated, and maybe therefore have a better chance of being successful. So he wanted to see if there was a connection between birth date and success. So we took a random sample of 80 National Hockey League players and wrote their birthdays down. Divided the year into 4 sections or 4 quarters, and here's where the 80 hockey players fell. Now you notice there's a lot more hockey players born in January through March than there are in October through December, but is that a fluke? Or is this convincing evidence that the birthdays are not evenly distributed among the 4 quarters of the year? So here's what we got. The null hypothesis is they're evenly distributed. The alternative hypothesis is they're not evenly distributed. I should mention this. I'm not a big fan of the way this sentence right here is worded. I would prefer to say it like this. Do these data provide convincing evidence that the birthdays of all NHL players are not evenly distributed? And the reason is this. If we're going to perform this hypothesis test, which is the way you should write it, the evidence is against HO, and we're weighing the evidence against HO, not for it, as this sentence right here kind of implies. There's no significance level given, so we're going to use 0.05. Now, this is 80 players So how many would I expect to be in each category? Well, if it's even, I'd expect a fourth of them to be in each category, 20, 20, 20, and 20. So let's continue with the problem. Let's check the conditions. It did tell me we had random hockey players. Is the 10% rule met? You might not know how many NHL hockey players there are. I certainly didn't. But you would say something like this. I'm going to assume there's at least 800 of them because it was 80 that I got times 10, and in which case I'm good to go. Large counts, do you expect at least 5 in each group? Yes, I expect 20 in each group. I expect 20 in each group because I expect the groups to be even, and I got 80 people. So now let's do the test statistic. It's each number minus the expected squared divided by the expected. I take these numbers and I add them up and I get 11.2. And again, you can do these in your calculator with lists. This is my chi-squared test statistic. What are the degrees of freedom here? 3. I have 4 categories minus 1. That's 3 degrees of freedom. And so I can use my chart to find that the p-value is going to be, since my test statistic is in here, my p-value is between 0.01 and 0.02. That's less than 0.05. So I do have statistically significant evidence that the birthdays are not evenly distributed around the 4 quarters of the year. I want to also show you, before I wrap this up, how to do this kind of problem on your calculator. So let me get that set up. All right, here we go. Now, if you have an older TI-83, it doesn't have this function, but our newer ones do. And it's not hard to do with a function or without. I'll show you both ways. So on my calculator, I'm going to go to my lists, and I can clear out what's there. And I'm going to enter these numbers. So there's my numbers. Now, in this particular case, I knew that those added up to 80, and I wanted a fourth of them in each group. If you can't remember what that is, you could actually multiply these out, and you could say, well, I know it's a fourth in each group. And that list, L2 times 80, gives me my expected counts. In this particular problem, you might not need to do that. You could do it in your head. But with the M&M problem, it would probably be helpful. Now what I've got are my observed values in L1 and my expected values in L2. So I'll do it first just with my lists. In L4, I'm going to make it, go up and highlight the L4. It's the observed minus the expected squared divided by the expected. Well, that clearly isn't right. Let me try that again. Oh, I know what I did. It's observed minus expected. My expecteds are in L3 squared divided by expecteds. Don't make that crazy mistake. See, these numbers were way different. These are huge numbers telling me that my observed and my expecteds were way different, and they're not. And more to the point, I know that this one right here, this second quarter, it was exactly what I expected. So that should be a 0. So that was my clue. I made a mistake. There we go. That's better. Those numbers will add up to be my chi-squared test statistic. So I go second, go list, math, and then add up L4. That's my chi-squared test statistic. And then, kind of like we've done on our other distributions, I can go second distribution, chi-squared CDF, and it's my answer right there, whatever that was. A really big number, 3 degrees of freedom. There's my actual p-value, which of course aligns with what I said over here when I got that it was between 0.01 and 0.02. Now let me show you one other way to do, and this is the way that some calculators don't have. But if I press stat test, and I go down here to chi-squared GOF test, goodness of fit test. That's what I'm doing. You'll notice there's another one here that's for tomorrow. I'll explain that later. Chi-squared goodness of fit test. My observes are in L1. My expecteds are in L3. Don't make that mistake. And I've got 3 degrees of freedom. When I hit calculate it, chicka chicka whir, there's my chi-squared test statistic, my p-value, my degrees of freedom, and my contributing factors right here. I'll explain what that means in just a second. But this is how you could do the same thing on your calculator. Remember this, for work, you're going to have to show something like this. So the calculator is great for multiple choice or to check your work, but you're still going to have to show. Okay, so finally, we've got a small p-value. We reject HO in favor of HA. Let me go forward to that concluding sentence. We have convincing evidence that the birthdays are not evenly distributed across the 4 quarters of the year. But this leads me straight into a question. If the birthdays aren't evenly distributed across the year, where is the difference? Where is it not like I expected? If you go back and you look at this list right here, these 4 numbers contribute to the chi-squared test statistic. This number right here is the biggest, obviously. It's the way biggest among all 4 of these, which means that the first number was the most different than expected. And that's because in the first quarter, I observed way more hockey players being born than I expected to see. That's why this number is so much bigger than the others, because this is where I was the most wrong or the most different from what I expected. That's the follow-up analysis that we really need to see in a chi-squared test. I've got another video of me doing another problem like this if you need to watch it, but hopefully a viewing or 2 of this will give you a good idea on how the chi-squared goodness of fit test works. Go Cougars.